Good evening and welcome to Distinctive Voices at the Beckman Center. I'm Susan Marty. And now to introduce our speaker is the other half of our Distinctive Voices team, Miguel Capinpin.
Thank you, Susan. The Ultimate Wave 3D is an IMAX film that follows a quest to find the perfect wave riding experience. Please help me in welcoming Dr. Hendrik Tolman.
Good evening. I'm glad I made it here. I woke up this morning in Washington, D.C., so I've had a little bit of a trip. So if I fall asleep halfway through, just remember I woke up at 2 a.m. So I was actually supposed to be the second speaker. The first speaker was going to be Linda Austin. She's a public relations person for NOAA and for the National Ocean Services. And she's the one who's worked a lot with the production company and with Kelly Slater along the lines of the movie, but also along the lines of public awareness. And so the first few slides are actually from Linda. So she's been working a lot doing education work, and it's kind of nice if you look at this movie because it's an IMAX movie. The idea is, of course, the surfers and Kelly Slater are going to be pulling all kinds of people into the movies. But if you look at it close up, it's actually much more an educational movie. It is really, at least half of it is about how islands are formed, what tides are doing, ecology, and of course where the waves come from and how can you surf them and why do you know they are there. What we did as part of NOAA is I was asked to help figure out ways of visualizing how waves get generated and how surf becomes surfable or not sometimes. And we've been working very hard with the movie makers to get extra exposure for the movie, like things at the National Ocean Week in D.C. We've been involved with the formal coming out of the movie, which already has been running here for a while, but it hasn't run on the East Coast yet. It's not going to show up there until the middle of October. And it is really nice to see that folks like Kelly Slater are not just focusing on their own capabilities of what they're doing, but they're doing quite a bit of work on public outreach for us and with us, which we really appreciate. We'll show in a little bit later, not quite now, but at the end of these few slides, a public service announcement that Kelly Slater made actually for NOAA, just to show you that it's kind of neat to be able to have well-known people help us get the message out. It's also kind of nice to know that this movie has really made some impact because it actually won some awards just a few weeks ago in Monterey. So with that, if we can do the public service announcement.
After the first rain of the year, a lot of people get sick because so much stuff washes out the rivers and streams. This isn't something someone else needs to clean up. This is all of ours. Even one person can make a difference in the health of our oceans. Please care. Get the facts and get involved at www.noaa.gov.
Thank you. If you can go to the second presentation, please. So why am I here? It took me a 7-hour plane ride to get here to show a 15-second clip. And a few more things like that. Well, I consider myself really lucky. I always wanted to be an architect. And because I wanted to be an architect, I figured out that I really didn't want to be an architect. I wanted to build stuff. So I became a civil engineer. And instead of building stuff, I decided it was way too much fun to sail and to be out on the water all the time. So I became a coastal engineer. And now I have the ideal job. I spent the last 20, 25 years of my life designing software for predicting waves. So I have the ideal job. I can go to the beach, sit back, open my eyes every now and then, and call it a day's work. How much luckier can you get than that? But more importantly, if I look around me and if I look at kids growing up, both in Europe where I grew up and over here, I'm a little disappointed to see that most of them are looking at going to college or to school to become a medical doctor or a lawyer, because that is where the money is to pay off their cost that they get into when they want to go to school. I find it a little sad to see that if I hire people, I have 25 people working for me, they represent 12 different birth nationalities. A reason for that is that in the US, we don't really educate enough Americans for going into science and engineering. Now, I love what I'm doing, and I like to show what kind of fun it is to do this kind of stuff. And therefore, I'm not going to kill you with equations and with all kinds of hard stuff. I'm going to try and show you how much fun it is to weave all these things together, because I'm officially a wave guy. So how can a civil engineer end up working for the National Weather Service as an oceanography? And oh, by the way, you know what my first job was? The obvious job for every civil engineer. I worked for NASA. So science can be really fun. My first job out of school was showing my parents a mock-up of a space shuttle and how they were training the robot arm there. And oh, by the way, this is where they built the space shuttle, the Hubble telescope. Great stuff. But why is a civil engineer working for the National Weather Service as a wind wave expert and as an oceanographer? Well, first of all, it's really not that strange, because most people in engineering that have something to do with waves are those people who work on the coast. And civil engineers, and particularly coastal engineers, are the ones who do that. So about 50% of the people who do anything with wave prediction in the world are all civil engineers. So it's not that weird. And it has to do with the fact that everything happens so close to the coast where the engineers work too. The other thing is, why do I do it at the Weather Service? Well, actually about 1974, UNESCO and the World Meteorological Organization had a meeting on safety of life at sea, and they came to the conclusion that waves really were a safety issue related to the weather. And as of that time, there are international treaties that require of every weather service that has marine responsibilities to do waves. So it is not at all a coincidence that I am doing wind waves as a civil engineer at the Weather Service. And why am I an oceanographer? Because the group that I'm doing is also doing, waves is only a third or so of the work we're doing. We also do ocean circulation, Gulf streams, sea temperatures, water level rise, all that kind of good stuff. So the one beef I have with scientists in general, and I now talk as an engineer because I'm an engineer and I'm proud of that. I'm more practical than a scientist, is that a lot of scientists think that they know everything. And that if they figure something out, they're the one that's invented it. Wave is a good example of where it's really not the case. Over the last 20 or 30 years, we've seen all kinds of science grow. We've figured out that waves and tides interact, that if there's a current, that waves do weird things, if there's shallow water. Guess what? Look at literature and art. Any of you have ever had to read the Odyssey by a guy named Homer from a few hundred years back? Ever heard the story of Scylla and Charybdis? Well, we all think now that actually is the water patterns around the Straits of Messina, between the tip of Italy and Sicily. Have you ever seen some of the famous marine painters from Russia? If you see how well they represent the sea, they obviously know what they're talking about, and they obviously know exactly what's going on. Nothing to do with science. If you've ever been at sea and look at a nautical chart, if you go like I used to do with a little 25-foot open boat sailing up and down the North Sea, if you go on the southern coast of England, there are a lot of headlands with very strong tidal races in front of that. Even in the 1700s, nautical charts already said, tidal race, do not come here. It's very simple. The mariners that survived would never want to go back there. Scientists, of course, never pay attention to that. They have to figure it out by themselves. Now, one of the things that I really like with waves, has anybody ever seen the way the Polynesians navigated from island to island? They actually use little things like on the right. Now that looks like sort of chaos to a lot of people, but the Polynesian navigators would put together from sticks a map like this that would depict to them how the different swell fields would curve around islands and things like that. The funny part is, only the people who made these things could read them. The neighbor next door on the other island didn't know it. But the point is, they would be reading the waves, and from the waves at sea, they would figure out where the islands over the horizon were. So again, way before we scientists figure out that you have refraction and diffraction and waves bend around islands. And oh, by the way, I got this beautiful satellite picture, and I can finally see that these waves are curving around the islands. Oh, by the way, these guys knew that thousands of years ago. So anyhow, having said that, there was really a need for going from general knowledge to really practical knowledge and forecasting. And the thing that really made wave forecasting become something important and interesting is D-Day. D-Day in Normandy, the Allied forces came to the conclusion that rather than taking a town and a harbor and using it, they would build their own harbor on the beach. But in order to build a harbor on the beach, they had to know whether they could do it or not. And so in this case, this became a real drive for some guys from actually around here to start looking at quantitative forecasting, what kind of waves you get, based on what weather you think you're going to get. Now, for that same reason, we at the Weather Service do wave forecasting. Well, as a Weather Service guy, I'm rather peculiar about what I'm doing. I have a computer model, but a computer model just gives a number. It doesn't give a forecast. It just gives guidance for people who can look at that to give the actual forecast. So as a forecaster from the National Weather Service, the person is always going to make the final decision of what the forecast is. The model is only a tool. So how long have we been doing this? The first computer-aided wave forecast was made 54 years ago. It was really simple. You looked at the weather chart, and based on the local wind, you would make one estimate of a wave height and one estimate of what kind of wave period would be. In effect, not much more than having a computer look up a number in a graph on a piece of paper. It took more than 10 years to come to the conclusion that the swell on the beach may actually be generated 1,000 miles that way by the wind there. So it took 12 years before the Weather Service went to predicting what the local winds would generate in waves and what the most dominant swell would be. It took another almost 20 years for the Weather Service to start looking at not one wind scene, one swell, but looking at the whole picture of all the wave energy going everywhere. It's what we call spectral wave model. I'll come to that a little later. And then for the Weather Service, the first model that really started using very high level mathematics was what we call the third generation model. It was another 10 years. And around that same time, I started developing the WAVEWATCH model, which I've been working with actually since about '86, but the third version of it was made for the Weather Service. So I'll get back to this computer modeling, but I will first use a few pieces of the movie to show you something about how waves are generated. And there's two different clips I'm going to use. There's one clip in the movie for about 2.5 minutes or 2 minutes or so that sort of takes you from very simple description of waves to how chaotic waves can be to how they're generated. And then the second clip will take us to what happens on the beach itself. So, having said that, can we please do the first clip now?
Small waves collide, sometimes canceling, and sometimes reinforcing each other as they organize into larger waves to carry the energy they have absorbed. The roughened sea surface increases drag and promotes more interaction with the moving air, resulting in larger waves. Bigger waves offer more surface to the wind. Growth becomes exponential. vast amounts of energy into the ocean. Wave energy can reach hundreds of feet below the surface and travel around the planet before colliding with land.
Okay, can we go back to the slides? I'll show this another time because this is a lot of stuff to look at, but there's an enormous amount of science behind this just 1.5 minutes. And what I really love to see is the fact that it's not just some wave guys trying to find some stuff, but one of the nice things of the wave field in science is that we've been actively borrowing and stealing from a lot of other fields as needed. And that's what I kind of like. So if you remember, and we'll show the clip a little later for a second time, it begins with a really nice, simple, smooth wave. You don't ever see these things, but that is stuff that was really liked by mathematicians. And the theory for how waves would run through water dates back to the 1600s. And around the 1800s, there was a guy by the name of Stokes who sort of made that really work well. And he didn't just make a just smooth wave, but he managed to make waves that were steep on the peak and flat in the trough. But it was still very, very much a very simple way of doing business. But interestingly enough, this very simple way of doing business is still the basis of all the models that we're running. Then you can see that you go from the simple motion to a very chaotic motion. If the wind blows very hard, you don't get a nice set of surf. You get an enormously chaotic surface, although it looks a little bit too chaotic in there, but it doesn't really matter too much. So it tells us that no two waves are the same. So why would you predict the wave height? If no two waves are the same, there is no such thing as the wave height. You have to do this sort of statistically. I'll come back to that later. What we figured out is that instead of trying to do one or two waves, we actually have to try and figure out how the wave energy goes in different wavelengths and in different directions. It's something that we call a spectrum. That was actually taken from theory that was developed for radios and for radio waves by a guy called Rice who worked for the Bell Labs, what's now AT&T. Then the other thing which is really interesting is that all these waves are interacting with each other, and I'll come back to that a little bit later. It's not something that we figured out, but it is something that comes directly out of quantum mechanics. So we borrow from quantum mechanics to make sure that we know how these waves all work together. And then some of the stuff I'm doing right now is because the quantum mechanics stuff is so complicated, we're starting to use techniques from artificial intelligence like neural networks, like genetic optimization, to build all kinds of better and faster ways of actually making these kind of models work. The other thing which is kind of interesting in this clip, you could see that the animators went from these lines to the dots to all the dots running individually. Now that was just a form of animation. But one of the very newer methods of trying to model the motion of water is not trying to look at this as a continuous mass, but as all little particles that just run into each other all the time. And a friend of mine at APL, Johns Hopkins, is actually running models now that run literally follow just all little blobs of water that run into each other all the time, which is very difficult to do in some ways, but also very interesting, because if it is little blobs, it doesn't matter if a little blob shoots out in the air and falls back in, which is something that's really hard to do. Oh, and by the way, for the younger crowd in here, what do you think sort of hardware they use for that modeling? Xboxes. Because most of the traditional modeling that we're doing, we try to mix being really smart in how we compute stuff with computing power that we have. If you start just following million particles, the only thing you really need is enormous brute force computing power. And that is definitely available in the Xboxes and all the stuff like that. And the other thing which I find kind of amazing is that when you saw the surface moving at the end, this is actually where the movie industry has helped science enormously in figuring out what to do. Because in order to make water look real, if you make it with a computer, it has to have the proper properties of reflectivity of light. If the light doesn't come off it properly, it doesn't look like a wave. And guess what? Radio waves and radar waves are not that different from light. So what some of the guys did in the movie industry is they helped us enormously in finding ways of how remote sensing with radar works from a surface of water. So let's see if we can take another look at the first movie clip. Can we just look at the first movie clip again now that we walk through them?
Sometimes canceling, and sometimes reinforcing each other as they organize into larger waves to carry the energy they have absorbed. The roughened sea surface increases drag and promotes more interaction with the moving air, resulting in larger waves. Bigger waves offer more surface to the wind. Growth becomes exponential. Storm winds transfer vast amounts of energy into the ocean. Wave energy can reach hundreds of feet below the surface and travel around the planet before colliding with land. Dangerous waving surf.
Okay, let's just go back to the other. I wanted to have it back at the first, but that's okay. Let's just look at some of the effects of what happens with waves. So I told you there is no such thing as a D wave. So what we normally predict is what we call the significant wave height, which is the average of the 33% of the highest waves. Now, which idiot came up with that definition? Well, it's very simple. It's actually something that looks like the highest wave when you just look at it. Because when you see waves at sea, what's the waves you see? You see the dominant ones. So if the waves are this high, do you see the little waves that are this high that ride on it? So you actually only see by your eye the highest 1/3 of the waves. But it has a little bit of a problem for me as a forecaster. So I have this guy in Maryland who has this beautiful boat, bought it, way too rich, doesn't know what to do with it. Has it in Ocean City, and he looks at the weather service and says, at the website, and says, well, wave height is going to be 5 foot. I can deal with it. So he goes out on his nice fishing boat. He puts up his drink and his caviar and stuff like that. And up comes these 9-foot waves and washes all his food overboard. So the next thing I get is, Dr. Tolman, your forecast stinks. You said 5 foot and I got hit by a 9-footer. Well, the problem is, I predict a significant wave height. If I predict a significant wave height, as in this case, let's say 10 meters or something like that, or 10 foot, then 1 in 10 waves is actually going to be a little higher. 1 in 100 waves is going to be almost half as higher. And 1 in 1,000 waves comes up to about twice as high. So if you look at how many waves there are in a storm and stuff like that, if I predict that you're going to have a 10-foot wave, then on average you'll get a 10-foot wave, but you better be prepared for that one from 20 foot. And this is a little problem that we have with educating the public, that when we say 10-foot wave, we may mean, you might get a 20-footer. And there's nothing we can do about it, because it makes no sense to try and predict the highest wave. Because sometimes the highest wave is twice as high, sometimes it's only 40% as high. So it's completely unpredictable. It makes much more sense to predict a more average wave. And then on top of that, if you guys want to have a nice other lecture, I can spend 5 or 6 or 7 hours on freak waves. The waves that are way higher than that, but no, I don't have time for that today. Other thing, talk about the amount of information that is actually in waves. Normally what you get is a little simple map like this. So this is the wave height, so guess what? There's a little dot there that is a little bit higher. So the wave height is higher, but the actual amount of information that our wave models have there is, we're looking at about 600 to 2,000 wave components, all different directions, all different wavelengths, and we try and figure out how the energy is distributed over them. So if you see a map from the Weather Service from a computer model that says the wave height is 10 foot, the underlying amount of information that we have is way bigger. And it's very important because if I want to know from that area there which waves are going to go to Japan, it's the waves that go in that direction. They may make surf in Japan. The waves that go in that direction will never see Japan. So a little bit about the physics. The clip already said that the waves basically generate an interaction with wind. Now, if you have wind going over waves, then the wind will pump energy in the waves, but the only thing it will do is make them higher. Because if you have 10 waves running behind each other and you have wind over that, if you want to make waves longer, you have to make waves disappear. Because you cannot suddenly have 10 waves in this distance and then suddenly have 5 waves in it and some waves are disappearing. Now, if all the waves try to go together, that will never happen. Same thing happens if a wave breaks. The wave will get lower, but not necessarily longer or shorter. So we do need to find and figure out what the mechanism is that doesn't make the waves just higher, but significantly longer. And that is where the quantum mechanics came in. This is where we figured out from the quantum mechanics that all different waves, when the wind blows hard and when the waves are high and steep, that they all interact with each other. And slowly but surely, the shorter waves pump energy in the longer waves. And as the longer waves start to exist, then the wind can pick them up and start making them grow really fast. And that's where the exponential growth came from. It also is really important for us in order to make the models work, because all this nonlinear interaction between all these different waves also generates very stable shapes of energy distribution over all these different wavelengths in different directions, which for us is important because otherwise we couldn't model this. So the movie only briefly deals with the transition from the real chaos to the wind sea, but to the swells of the coast. But I'll go a little bit faster through that here. The issue is that waves are dispersive. If a wave starts running in that direction, it will follow a great circle in that direction until it hits shallow water or it hits a person in the audience or the coast. Along the same line, a wave that is this long travels significantly faster than a wave that is this long. So if I have a storm far offshore, the first thing I will see is the very, very long swell. And the longer I sit here, the shorter the waves are going to get. And that is something called dispersion. The interesting part of it is that those waves actually can travel around the world with almost no internal friction. So once a wave is generated, it keeps running until it hits the shore somewhere. That's why almost always there is some kind of surf on the beach, although it may only be that much. Now, why are those swell waves not as high as the ones in the deep ocean of the storm? Because the dispersion patterns make that you start with a very little area where all the waves grow, and then literally the energy gets distributed over the entire ocean. So the problem is that swell is spreading out so badly, and only very close to the coast does it get very high again. So it's kind of nice to have the capability of doing things in, wrong one. This is a picture of wave energy that we observed and modeled for Hurricane Isabel in 2003. So this is September 8, 10, 12, 14, 16. These are all the different frequencies. So this is very low frequency, very long waves. And the waves get higher frequency and shorter. And the more rare it is, the more energy you see. So at some time on the 12th, I see waves showing up here that are approximately 20 seconds between crests. And the longer I wait, the shorter the waves get and the closer they get together. And this is kind of neat because if I just draw a line through there, you can do the math and you can figure out very easily that right here is when all the waves were generated in time. And since you know how fast these waves are running, you can actually figure out exactly, if you know the direction where the waves come from and how they change their period in time, you can figure out exactly where they came from. In 1966, there was a experiment done out of Scripps here called Waves Across the Pacific, where they had several measurement locations through the South Pacific to see if they could figure out whether the swell really run along great circles and very well. They were doing measurements just here on the coast or in La Jolla, and they actually managed to measure with this behavior of waves that were generated literally on the other side of the earth, south of India, in the Indian Ocean. They had run all the way south of Australia, between Australia and New Zealand, and had been arriving here very simply predictable at the coast. And that was done in 66. Now, this is kind of nice. If I have a model, I can do some experiments that I can never do in nature. So what I did here is just start my model with saying, okay, there's no waves whatsoever. And then I start the wind to blow. Now, of course, the wind blows, I thought I had one of these things, really only in the southern hemisphere and the north. So the top and the bottom is where waves are being generated by the wind. Now, what you see here is not the wave height, but the wave period. So at the beginning of the cycle, there's nothing there. And if you look very closely, the red is a very long wave, 18, 19 seconds. This is like 15, 16. This is like 12, 13. You can see the pattern where the long waves run first, and then the shorter and shorter waves come behind it. And this kind of dispersion patterns you can see all through the ocean. So, what is different at the coast? Well, the chaos you see when wind-generated waves is not something you can surf on, ever. You need a nice set of waves that are regular. So what happens due to this dispersion is that the chaos from the generation gets moved into the organized sets of waves that you see on the coast. And the bigger the ocean, the longer the sets. So the seventh wave is something from Hawaii. If you would do the same thing on the Atlantic Ocean, it's probably the third or the fourth wave. The sets are a little shorter. So some of this waves on the beach you can still describe exactly the same way I described waves in the deep ocean, with the distribution of energy over all directions and all the wavelengths. But really, if you do that, you can still do very decent waves on the coast. And again, it's a place where we borrowed something from another piece of science, because the way waves focus around shoals and around headlands is very similar to how light goes through lenses. And we literally use what we call a geometric optics approach. And if you have done your physics classes, you probably ran into Snell's law somewhere about, well, guess what? There's a Snell's law for ocean waves too. So that is how we can figure out where the focal areas are on the coast and where the bigger surf is. But what you really need to do is you need to go, instead of trying to sort of statistically describe it, try to describe these waves one at a time. And that is a way more expensive way of doing business, and it's not something that we will do in a real-time basis for the Weather Service in the near future. So, do we have the second clip at 3434 ready? I would like to show that.
We're falling altogether.
I need to be at 3434.
You have to pick.
Well, if you find that, then I'll go on with this for now. So this is basically more or less about all the bits and pieces in the movie. What we do with our wave forecasting is really focusing on the deeper ocean, and there are many local organizations that will give you a good surf forecast based on what we are doing, and it's kind of interesting to see how that works. It's not really the science side of it, but it's really the fact that we have this public-private partnership in weather that sort of plants itself forward into the waves too. We basically focus on raw products, so if you see relatively crummy graphics from my website, there's a reason for doing that. I am supposed to be only putting out the raw data so that the people who want to make a living out of that can still do something of that. And we do put our stuff out on the website just because of the Freedom of Information Act sort of forces us to do that. But we're sort of walking a very thin line. We cannot spend much, I cannot spend much time on making a really nice, good website that looks really glitzy and gives you all the details of each beach you want. But I really don't want to do that either, because that sort of takes away from the bigger picture I need to do. And it's not like I'm hating these guys. They actually have been some of the best advocates that I've ever had for my work. So we have a very nice thing there. Do we have it? There we go. So this is about the transition on the coast.
Outrun slow ones. The waves become organized into sets. Local winds, currents, and tides play their part in shaping the arriving swell. The sea bottom plays the most critical role. A gentle slope produces gently breaking waves. A sudden shallow can produce a plunging breaker. A shifting sandbar or a coral reef, a seamount or a rocky outcrop, each has the potential to shape surfable waves. Like a lens, the shape of the bottom can focus or diffuse the energy of the wave, change its course, or stop it altogether. A sudden shelf and shallow reef compress the arriving wave energy, dramatically increasing wave height. As the wave slows, its crest continues to swoop forward, generating a great cathedral-like barrel that breaks across the reef with perfect symmetry.
So that was in a nutshell about, I would say, 50 or 60 full careers in wave modeling. So I have a little bit less experience with that part, since we do the bigger picture, but that is what really makes the waves surfable. And this makes it so that you can stand at Oahu at the North Shore, you can look over the ocean and you're standing on the beach and think, well, there's nothing happening here. And then you have absolutely no waves there, and you have absolutely no waves there, and you have the Banzai pipeline right in front of you, only about 200 foot wide. And so the point is with surf prediction, what we do is we predict the offshore conditions just a little bit outside of the surf zone. But it requires local knowledge to understand what is going on with the waves actually at the beach. And probably in 10 or 15 years, we will come way closer into the coast with our models, but there will be always place for local knowledge, either very high-tech or even very low-tech, to be able to do this local forecasting. Let me see, I don't have that much time anymore, so I'll go very quick through these ones. I actually just leave these for what they are. So we have some time for questions. The only thing I would like to show is a little bit about some of the need, if you're in computer and in animation and in predicting, you'll understand some of the problems we have. The National Weather Service has responsibility for forecasting from here to the right and from north of the equator. And oh, by the way, all these little green dots are all countries that we have responsibility for training them. So if you go in the deep ocean, it's good enough to know how the wave field changes at the scale of about 50 kilometers or 35 miles or so. If you look in the yellow areas, the offshore areas, which is typically about 200 miles, 250 miles offshore, we have to do a much more detailed weather forecast and wave forecast. And then in the little offshore area, some 50, 60 miles offshore, or sometimes 20, or the Great Lakes, we have to do forecasts at the scale of making a distinction between wave conditions at about 2 kilometers or 2 miles. So as a forecaster, how am I making a model that gives guidance to all these people at all these scales? So what we're doing is we build a whole bunch of different grids, and instead of having one model that runs very coarse and one that runs very, very detailed, I let all these grids talk to each other, and all these little models become, in essence, one big model. So if you look at this picture, that picture, yeah, If you look at that picture, which shows how detailed the model is. The model is detailed at about a 50-kilometer scale here. In the blue, it's about a 18-kilometer scale, and in the red and orange, it's about a 7-kilometer scale. And so we are able to make a model nowadays that this is the lowest resolution. So this is about the 50-kilometer resolution. But in this area, the white area, I was not really calculating at that level of detail. I can actually get a much higher level of detail. And so if you overlay that, you can see that that seamlessly fits in how things are going in the offshore. And then really close to the coast, I'm now doing things at about 7-kilometer distinction between what's going on. And if you overlay that, you can see that all these different products all work very smoothly together. And now I can only say about every 7 kilometers along the coast what the wave conditions are going to be. In about 4 or 5 years, it will be about 1 kilometer. We are now actually testing models that we're running that can tell you the difference between wave conditions 100 meters apart along the coastline, 300 foot. I need a little bit more computing power for that, so if you see your congressman, please tell him I need more computing power. But we'll get there. So anyhow, I hope that you've enjoyed this, that you've learned something from it. If you want to know more, this is the website of the Weather Service where we have all our models. You can take a look around. If you don't believe in those crazy scientists and their computer models, you can go directly to the source. NDBC stands for the National Database Center. They have a fantastic website that you can get observations from all over the world about the waves, what they are looking right now. But it's not completely ideal. These guys have not figured out yet how to measure tomorrow's waves. So you'll probably need us a little bit too. Anyhow, thank you for your attention.